students, today we will discuss electric flux calculation for a point charge by using a solid angle. In my previous video, as I discussed electric flux through a disc by using an integration method. So, this is by using a solid angle. It is the simplest method we can say. Consider a point charge is placed at a distance L from the center of a disc of length L. The disc is having a radius R. Then the extreme ends, if I observe over here, the electric field lines passes through a disc looks like a conical shape. Then the half angle of a conical shape is phi. Then the angle represented over here is a solid angle. As we know that relation between a solid angle and then half angle of a cone is that 2 pi under root of 2 pi into 1 minus cos phi. Here, as we know that for a point charge, the electric flux through a complete spherical surface, if I consider at a distance q upon epsilon naught, electric flux is equal q by epsilon naught, and the solid angle in this case is that 4 pi steradian. Q by epsilon naught is the total flux due to this point charge at a distance r, we can say. So, for a 4 pi steradian, Q by epsilon naught is a flux. Similarly, here for a solid angle over here omega, how much flux is present? To analyze over here that for a 4 pi steradian, the flux due to the point charge is q by epsilon naught. For a solid angle is how much? Then omega, for a solid angle omega, the flux phi dash, if I indicate that omega into q by epsilon naught upon 4 pi. Since we know that omega is equal 2 pi into 1 minus, by seeing the diagram cos phi is equal adjacent side by hypotenuse, that is L by root of L square plus R square. Then in place of omega, if I substitute, I will get over the flux due to the solid angle 2 pi into 1 minus L upon root of L square plus R square in place of omega, as it is q upon epsilon naught by 4 pi. 2 gets cancelled. Then finally we will get flux through the solid angle or flux through the disc of radius r will be q by 2 epsilon naught 1 minus L upon root of L square plus R square. As I have discussed in the last video, by using an integration method, the result will be remain same. So, one more example we will analyze by using a solid angle, how to use. Let us suppose a point source, a point light source having a power has 100 watt, having a power as 100 watt is placed at a distance x from the center of a hole over the cardboard, you can say. At this point, the radius of this hole is r. A point source of light at a distance x from the center of the hole x. Then find the power passing through the hole in this sheet. Then a point charge or a point light source, charge or light source, we can take an example, having its power as 100 watt. So, if you assume over here this 100 watt power generation are radially outwards for a solid angle of 4 pi steradian. For a solid angle 4 pi, this 100 watts is there, because the light source provides in all the directions. The light source emits the light in all the directions. So, for a 4 pi solid angle, as we know that solid angle is a 3-dimensional measurement. For a plane angle is a 2-dimensional measurement. So, 4 pi steradian 100 watts is there. Then from this point, the light passes through the hole, maximum amount of light passes through this as this much solid angle, you can say. Over here, the solid angle as omega I am writing. Then as we know that the half angle of a cone with relation as solid angle, let us suppose phi is the half angle of a cone. Then the relation we know that omega is equal 2 pi into 1 minus cos phi. And omega is equal 2 pi into 1 minus, in place of cos phi, adjacent side upon hypotenuse, x square plus r square. So x by x square plus r square under root. So this will be the solid angle subtended over here. Then for a 4 pi steradian 100 watts of light it is there. For omega is how much? If I say for omega how much? For omega is the solid angle as we have discussed. Then we can write over here that the amount of light passes through this hole of radius r from for the sheet into 100 upon 4 pi. It is a very simplest way to use or to solve the problems by using solid angle concept. So in place of omega I can write over here 2 pi into 1 minus x by root of x square plus r square into 100 upon 4 pi. So gets cancelled with 2 with 50. Then the amount of light passes through the hole. This is the amount of light passes. Amount of light passes through hole. It is nothing but we can analyze like a flux, we can say. Amount of light passes through a hole is equal here 50 into 1 minus x upon root of x square plus r square. This much light passes through the hole, 50 times 1 minus x by root of r square plus x square. And one more example also we will consider. Here one more example if you consider, there is a point charge placed inside a cube at the center of the cube. A point charge q placed at the center of the cube. And then the flux through the cube, if I consider flux through the cube, this will be the center of the cube, we can say. The flux through the cube, if we consider that, before that flux for a solid angle 4 pi, we know that q upon epsilon naught, flux through due to a point charge for a complete solid angle here. It is a 3D measurement. Same thing over here also. For complete cube if we consider, the solid angle will be equal to 4 pi. So for a 4 pi steradian, the amount of flux passes will be q by epsilon naught. Then this 4 pi, totally how many phases are there if we consider? Totally 6 phases are there. So for a 6 phases, complete 6 phases, the flux is equal to q by epsilon naught. So the flux completely through the cube is equal q by epsilon naught due to this point charge. For a one phase of the cube if we consider, so for a one phase of the cube if we consider, here are 6 phases we should divide. When you divide the 6 phases, that is 4 pi by 6 is the solid angle, we can say. The 4 pi is the solid angle for completely 6 phases. For each phase if I say, we can say that 4 pi by 6. So for a 4 pi by 6 solid angle is how much? Then 4 pi by 6 into q by epsilon naught upon 4 pi. Then we can say over here that q upon 6 by epsilon naught, flux through each phase. In generalized condition we can say that the total for the cube, the total flux is equal q by epsilon naught. For each cube if I say the 6 phases are there, the 6 phases will be distributed equally q by epsilon naught upon 6. So q by 6 epsilon naught we can say. So this is the way to analyze by using a solid angle. Now we will enter into the concept of Gauss law. So before discussing the concept of Gauss law, over here flux, one more example I will take. The one more example if you consider that there is a hemisphere over here, I am considering one hemisphere, closed hemisphere, contains a charge just outside the closed hemisphere, the charge is present over here. For the center, just outside. So another kind of analysis over here, if you say just inside, the charge present for a closed hemisphere just inside. and exactly center of the hemisphere if the charge present, if I say exactly center of the hemisphere, then the flux through the charge which is present outside, if you see whatever the flux entering as well as exiting, as we have discussed in the previous video that when an electric field lines are enters through this surface, here area vector is normal drawn, the flux entering is negative. The amount of flux is equal E bar dot A bar, that is EA cos 180. Cos 180 is minus 1, so flux entering will be negative, we can say. Whatever the amount of electric field lines obviously exits with this second surface over here. Here E bar and area vector both are in the same direction, theta is equal 0, the flux exiting will be EA cos 0, it is a plus EA. So this is entering and here as exiting. So the total flux linkage through this cylinder, that net flux or total flux is equal 0, we can say. The same thing over here also, since the charge is present outside, how many electric field lines are enters, those many electric field lines exits. So the total flux linked to this hemisphere is equal to 0, we can say. And flux due to the point charge just slightly inside over here, as we know that flux due to the point charge is Q by epsilon naught, and it is independent of shape of this closed surface. So obviously the flux due to the point charge will be equal to, we can say over here that Q by epsilon naught, we can say. Since the charge is exactly placed at the center, if you observe over here, we need to close completely first initially. When you are closing over here initially, we have to close. I am going to discuss in a Gauss law why we should close. In these two cases anyhow you analyzed, and the third condition why we should close, in a Gauss law it comes. So when we close over here, then flux for a completely this sphere, if I say Q by epsilon naught, for a complete sphere, Q by epsilon naught. But here two hemisphericals are present, one is above the upper half and below the half hemisphere. So the flux will be distributed over here, that then flux through the half sphere, because we require to find through half sphere only, so it will be distributed by 2. So that is Q by 2 epsilon naught, upper Q by 2 epsilon naught, the down Q by 2 epsilon naught. So the total will be equal to Q by epsilon naught for a complete sphere. Since over here half hemisphere, Q by 2 epsilon naught. This is for hemisphere, half sphere or hemisphere, we can say. So now we will enter into the Gauss law. What is analysis of Gauss law? If you consider, the Gauss law is a mathematical analysis or a mathematical treatment to find the electric flux from a closed surface. So Gauss law is a mathematical treatment to find electric flux, from a closed surface, the Gauss law. So Gauss law is applicable when the electric field lines are emerges from a closed surface. So electric field lines are emerges from a closed surface. Generally the electric flux, if we consider, we know that for a closed surface integral E bar dot dA bar or ds bar, the total flux to a point charge, if only one point charge is there or number of charges are there, is equal 1 by epsilon naught times the net charge enclosed within the closed surface. Within the closed surface, let us suppose I am taking a closed surface, there is a multiple charges are present over here, if I say. Let us suppose like these charges are there, all are positive charges I consider. Then the Gaussian surface, whatever the closed surface I said you, this is called a Gaussian surface, we will say. Gaussian surface. Here Gaussian surface, why we consider that the total flux enclosed within the surface, the total flux enclosed within the surface is equal 1 by epsilon naught times charge present within the surface, we can say. So, this closed surface will choose, this closed surface is called a Gaussian surface. In simplest format, the Gaussian surface either spherical or cylindrical according to the charge distribution, we can say. If we consider a random distribution of Gaussian surface, then when you are finding a closed surface integral E bar dot ds bar, is a completely closed surface. When you are integrating, it will be a complex. So, to avoid the complex, we consider a simplest form of Gaussian surface, either cylindrical or spherical, mostly we will use. So, here spherical or cylindrical, first of all, if you consider when you want to find the electric flux within this surface, we will consider over here that flux due to these charges only. The electric flux is present due to these charges. Whereas, when you say the electric field at the surface over here, the electric field is net field, we can say. When you are using the electric flux concept, this E is a net electric field, we can say. So, the net electric field is E bar dot ds bar gives the flux. So, E bar is the net field on the surface. So, the significance of Gaussian surface, if we consider here, is that within the closed surface, the flux link enclosed, that is due to inside the charges. So, according to Gauss law statement is that the total electric flux enclosed within the Gaussian surface is 1 by epsilon naught times charge present within the Gaussian surface. The Gaussian surface, while you are choosing over there, where you want to find the flux or electric field, at that point the Gaussian surface must touch the surface, and over that point the flux is due to enclosed or within the charges only. Over that surface at that point, the field will be a net electric field, we can say. And while you are choosing the Gaussian surface, keep in the mind that electric field should be at that surface, at that point, either uniform or 0, either uniform or 0. Electric field should not be changed from that surface, from one point to another point on the surface. And electric field should be either parallel, that is tangential to the surface, or perpendicular to the surface. Either parallel to the surface or perpendicular to the surface, anything should be there. So, the electric flux, when you are finding over here, we need to choose a Gaussian surface according to the Gauss law. When you are choosing the Gaussian surface, their electric field either uniform or 0, or electric field either parallel or tangential to the surface or perpendicular to the surface. And here electric flux is equal to 1 by epsilon naught times charge present within the Gaussian surface. So, here electric flux is due to charges inside the surface only. So, according to this surface, if you see electric flux, when you are choosing over here, when you are finding, it is independent of the shape, and whatever the shape is there, 1 by epsilon times charge present over here, Q1 plus Q4 plus Q6. But when you are finding the electric field, we will take care about the regular or known surface, it should not be a random surface. So, if it is a random surface, to find the electric field is very complexive. So, to avoid the complexive, we will choose a particular suitable surface in easiest method. So, the enclosed within the surface 1 by epsilon times the total charge. If it is a negative charge is there, let us suppose here minus 4 is there, if I say, then in this place also we should write minus Q1 minus Q4 plus Q6. It is an algebraic sum of charges, we can say. So, this gives the electric flux due to the Gaussian surface. Now, by using Gauss law, first step we have to analyze where you are going to find the electric field, there we must take the Gaussian surface, and over that electric field we can find. Over that surface the electric field is a net field, and within the surface the flux will be due to enclosed charges, we can say. Now we will consider the applications of Gauss law. The first application of Gauss law, if we consider that, electric field strength due to a point charge. For example, if I say there is a point charge over here plus q placed, only one single charge, and I want to use the Gauss law to find the electric field over here at a distance r, at this point P I want to find. It is also, we can say, the derive Coulomb's law from Gauss law also, we can say. The first application over here is that electric field due to a point charge. As I said you just now, that where you are finding the electric field or where you are to find the electric flux, so there we should construct a Gaussian surface. That Gaussian surface should be an enclosed, and to find the electric field it should be a simplest method. So to analyze over here, I am considering the Gaussian surface is a spherical surface. I am considering this will be the spherical at a distance r. At any position the distance remains r, you can analyze, if you can consider over here that electric field should be uniform. At any position over here the direction of electric field is radially outwards. So the point charge is inside and the Gaussian surface is like a spherical, like a globe, we can say. It should be a symmetrical, Gaussian surface should be a symmetrical. Since over here is a symmetrical over here, at any point if you see the electric field lines on the surface should be radially outwards, and the area vector should be also along the direction of electric field only. So the angle between area vector and electric field will be 0. Then over here within this enclosed surface, first we can find over here electric flux. So as we know that electric flux according to Gauss law, 1 by epsilon naught times charge present within the Gaussian surface. So within the Gaussian surface the charge present over here is plus q. Then the electric flux is equal to, we know that the circle represents the total surface integral or closed integral, we can say, E bar dot ds bar. Then the electric flux is equal to E ds cos 0, we can say. Here if you assume, if we can consider that here electric field is a uniform, as I told you just now, electric field is uniform, either perpendicular to the direction of surface or tangential, it is anyhow perpendicular. So E ds cos 0, then the electric flux is equal, E is a constant, integration of ds. Then the total surface, since it is like a spherical, so we can say over here E into 4 pi r square. So electric flux is equal to E into 4 pi r square. Since Gauss law, electric flux is equal to q by epsilon naught. So E into 4 pi r square is equal to q upon epsilon naught. Then the electric field intensity due to a point charge 1 by 4 pi epsilon naught q by r square, when I brought over here 4 pi r square in the denominator. So this is the electric field intensity due to a point charge, already we have derived this point. Suppose Coulomb's law, if the question asks over here, derive Coulomb's law from Gauss law. At this point where you are going to find the electric field, if I place a point charge as q naught over here, at this point if I place a q naught, then it is a small positive test charge, of course you can say. Then on this plus q naught, the force act in the direction of electric field. So force is equal to q naught into E, we can say. Then the electric force is equal to q naught into 1 by 4 pi epsilon naught q by r square. Then by using Gauss law, the derivation of Coulomb's law will be 1 by 4 pi epsilon naught q naught by r square. Up to electric field due to a point charge here only, and by using Gauss law, derivation of Coulomb's law will be up to here, we can say 1 by 4 pi epsilon naught Q1 Q2 by R square, that is Q into Q naught by R square. This is the first application, that is electric field due to a point charge, we can say. Now we will discuss over here electric field strength. Electric field strength due to a long charge wire. The second application will work over here now. Electric field strength due to a line charge or infinite line charge or long charged wire. So consider a wire having a long charged wire, a line charge, we can say. So it is a long charged wire, uniform charge density, you can say. Here uniform charge density lambda is linear charge density. So I want to find electric field intensity at a distance r from this line charge. So as we have discussed in my previous videos that electric field intensity by using a very integration or derivation method we have done. So without using that, we can use over here by using Gauss law. As I told you, where you have first Gauss law, when you are applying, we have to construct the Gaussian surface. So where we should construct the Gaussian surface? That surface must touch the point P where you are going to find. So, and that surface should be in a simplest format. So the suitable Gaussian surface for this, I am choosing over here that a cylindrical surface I am using, cylindrical Gaussian surface I am using. This is a point P, of course. So the cylindrical Gaussian surface is having a radius r and length over here is L. Length over here is L. So the length of this Gaussian surface is L and radius is r in a cylindrical shape I used. Then here over this, what is the direction of electric field lines? Here totally 3 surfaces are there. 2 circular surface and 1 is curved surface. Suppose if you see over the top surface, the direction of electric field lines will be tangential to the surface. On the surface we can analyze over this surface. The top surface is tangential and bottom surface is also same thing, we can say over here, tangential to the surface. And here area vector, if you assume over here that area vector for the top surface, it looks like this. The top surface, the electric field lines are tangentially over here, the area vector is outside and electric field is tangential. So the angle between the electric field lines and area vector is 90 degrees. Over here is also at the bottom, if we consider over here, the direction of electric field lines are tangential to the surface and here area vector is downwards. So here angle between electric field is tangential to the surface and area vector is perpendicular. Then the angle between electric field and then area vector is 90 degrees over here. So that electric flux due to the circular surfaces will be 0. But for a curved surface, if you consider, the electric field is perpendicular to the surface at any point radially outwards. There is a line charge, if we consider over here, this is a line charge and over here positive charge is there. If I say at any point, if you see, the direction of electric field is radially outwards and the surface, if you see, it is a symmetrical distribution. So that any position, if you see, it is a symmetrical configuration. So that here area vector is also for a small elementary part, if we consider. So area vector and electric field both are same direction. Angle between these two is 0, of course. So the electric flux is present due to only the curved surface, we can say. So for a curved surface, this is for circular surfaces, circular faces, you can say, the top end and bottom end, first end, second end, third end. So this is for first end and second end, electric flux is 0. For a third one, that is a curved surface. For a curved surface, third one, the electric flux is equal integration of E bar dot ds bar. which is equal to 1 by epsilon naught times charge enclosed within the Gaussian surface. So, here at a given distance r, each and every position, suppose due to this small elementary part if you see, the electric field is E, the distance is constant throughout the surface, so the electric field is uniform for complete circular surface. So that electric field is a constant, that is our primary condition, either electric field should be uniform or 0, here electric field is uniform. And second condition should be either electric field will be tangential to the surface or perpendicular to the surface. So, top ends it is a tangential, for curved ends it is a perpendicular. So, that two conditions are satisfied. So, we can say over here E ds cos 0 is equal to 1 by epsilon naught times, here total charge, here linear charge density is lambda over here, lambda is equal to within the enclosed surface over here Qn by length of this over here L, I consider length of the Gaussian surface is L. Then the charge present within the Gaussian surface will be lambda times L, we can say. So, I can apply over here lambda times L. Then cos 0 is 1, electric field is a constant, we can bring out over here. If the electric flux, if they ask, lambda L by epsilon naught, but we need to find electric field due to a line charge, E integration of ds is equal lambda L upon epsilon naught. Then electric field into what is the total surface area of this cylinder if we consider 2 pi r L, we can say the Gaussian surface, cylindrical Gaussian surface area is 2 pi r L is equal to lambda L upon epsilon naught, L gets cancelled. Then the electric field intensity due to the line charge is equal to 2 pi epsilon naught r, we can say electric field intensity due to a line charge will be 2 pi epsilon naught r, lambda by 2 pi r epsilon naught. Here if you observe over here, electric field intensity is inversely proportional to r, as we have discussed already the graphical representation E versus r, the graph will be like this, it looks. So, the electric field due to a line charge, we constructed the Gaussian surface as a cylindrical, and this is the basic idea. And in my next video, I am going to continue that electric field intensity due to a hollow cylindrical charge distribution or solid cylindrical charge distribution, and then continuation. Thank you.